Okay, it's noon time, actually 12:30 Central Time. Okay, today we are on lecture 10, tokenization. But before we go to the tokenization, let's go back to the lecture 1. Okay, lecture 1. So this course, our main purpose is to introduce programming languages. So we finished structural programming. Okay, structural programming. We finished the object-oriented programming. We finished three lecture on functional programming, including Python, recursion, and skip. Now we are on the last unit, that is compiler design. Okay, language translation. That's core for this course. So we talk about different programming paradigms. No matter what feature your language may have, now it's time to talk about this translator. How you take the language in and then compile to executable code or create a program to run it. That's interpreter. Okay, so we are on the last unit to design, to know about the structure of this translator now. So basically, before we jump to the tokenization stage, let's look at the overview of the compilation that is in chapter 1. Chapter 1, we actually did not go through the slides when we start because it's supposed to be easy, and we will do it now. Go through a few of them. So basically, chapter 1, we talk about different programming paradigms, declarative, imperative, okay, and then imperative, functional, object-oriented, and we use several weeks to talk about this. So that is done. Then we would talk about the interpretation of computer programs. This is the core knowledge that we need to learn for this book, right? The book is called The Structure and the Interpretation of computer programs. So basically, it's talking about translation. Okay, and then translation, we have three typical examples: Python, Java, and C++. Okay, these three languages are typical because number one, if you are in C language, you are pure compilation. So you have source program in, translated to the executable code out. .exe. Okay, nowadays you may be able to translate to lower level virtual machine code. It's possible, but most of the time you are translating to the packet executable code. Okay, so that's pure translation. And then is that okay to compile C to Java? Yes, you can compile C to Java and then run on Java virtual machine. So many, okay, this is pure translation, but basically pure translation is translated from one language to the other, especially from high level language to executable code. Okay, so this, another type is pure interpretation. So pure interpretation and the pure compilation. Pure compilation is C++. Pure interpretation is Python. So Python has a source program, and then with input and you create output. So this one is every time you have greater than, and then you type in A equals 3, you interpret it 3, and then B equals 4, and you interpret it and you get 4, and then print A plus B, and then you interpret it, and then it gets print 7. Okay, so that is pure interpretation. That means you get the program in, and then there's a Python virtual machine here. Your language being run on a virtual machine, and it give you 7 right away. So that's actually an interpreter, but every line of the code being translated once, and that's interpretation. So this is pure interpretation. That typical language is Python, JavaScript. Okay. Now this one, okay, interpretation has greater flexibility, better diagnostics. You can run and then using shell to know about the current errors, but it will be slower compared to compilation-based C++. And then there's a hybrid type. Hybrid type is the Java. Java, you have source program translated to the intermediate program, we call it bytecode. And the bytecode with the input run on Java virtual machine. And then you create output. So this is hybrid type. And typical hybrid type is Java. Java has Java virtual machine. And then your source program translate to intermediate program and then run with Java virtual machine. Okay. So Java program compared to Java bytecode program. And Java bytecode program is a intermediate code. And this one can run on the Java virtual machine on Mac OS, can run on the Java virtual machine on Windows, also can run on the Java virtual machine on Linux. Because of these, Java program is portable. That means that you can you actually can run on any machine that has Java virtual machine on. Okay, so that's the advantage of using the virtual machine. And in fact, Scala, several languages are actually, so programming languages using Java virtual machine. So they are about more than 200 languages. They are on top of the Java virtual machine. And we call it JVM languages, okay? JVM languages. So typical JVM language is like your language actually is another language, but you compile to Java, the bytecode. So Java, Kotlin, Groovy, Clojure, this different JSON. Okay, I think this one is Java style Python. JRuby, okay, whatever. Okay, actually compared to CSON, okay, CSON, C base. This one with it actually creating Python on C++ is actually executable code. I believe this one is actually faster. And then I think this JSON probably run on Java virtual machine. I never run it before actually, but I think it's still Python, but just run on Java virtual machine. Okay, so these are the virtual machine versions. Okay, so Kotlin very famous, Scala very famous. Okay, these are typical data science type of the program. Okay, so these are the language that Java virtual machine. I post this one in chat box. Okay, so the language design, you actually have to choose pure compilation that is totally not portable, like C++ for the speed, or you choose to become pure translation that give people the quick response and easiness for debugging. So this one is Python and JavaScript. Or you choose to be intermediate, hybrid. You actually have the bytecode and being portable on Java virtual machine. These are different choices when the language being developed. Okay, so now go back to the interpretation of computer programs. So we choose one way to compile, and then we need to choose the way to design the translator. Okay, so the translator can be a compiler, can be an interpreter, can be a hybrid version. Okay, so let's look at the pure compilation. Pure compilation is C++. It too has a preprocessor to process the directive, such as the include file, okay, and some definition for the constants, okay, and the define undefined these different things. So your source code goes through the pre-processing, and then everything becomes C, okay, and then do compiler, and then get object code, and then link, and then executable. So it actually goes through the compile, link, Go process. Okay, this type of compiler is compile link. Link is actually hook up the jump edges for the functional call. And then finally, you need to use a runner to run it, okay? And it actually using executable code. So it's a compiling Go process. This is a typical traditional way of programming. And somebody say that actually this is pure programming. This is real programming. C++ are the only programming language in some people claim that because they really create new program to run. Okay. And you run on Java virtual machine, it's not a program. You run on Python virtual machine, that's not a program. So C++ is really creating executable code and run on Token machine. That is programming language. Some people claim that, okay. Okay, so this is the traditional way of doing programming, and then you need to use a compiling Go, and so there's a library, and then the library routine nowadays becomes standard template library, okay, for C++, and you link and Go, and now linking originally is compile time linking. We call it static linking, and then later become dynamic linking. So you do have the DLL files, okay, something like that. And then post-compilation assemblies. You can also compile your C++ to become assembly code. And then you use assembler to assemble to machine code. That's also okay if you prefer to develop a system in assembly code. And then preprocessor can do conditional compilation to modify the source code to a different format. For example, adding more code to it, okay, and swap some code, okay. And so to source translation, so you can also do source code C++, target code assembly. It's also possible, okay. These are different compilation. Now let's look at the interpreter approach. Interpreter, you can compile into a interpreted language. This one actually is from Python to the PYC. PYC is a bytecode for Python. And then this is precompiled code sometimes can be loaded, just like you use the Python library, a Java library, and can run on Python virtual machine, okay? So that's a compilation of interpreted language. You can still prepare the PYC code, okay? That's actually pre-compiled code. And virtual machine use a just-in-time compilation, means like they don't really run it or compile it before you are running. Okay, that's called just-in-time compiler. Just-in-time compiler means that your Java code really create a .class file that's actually bytecode, and then when you run it, when you load the class to the Java virtual machine, the just-in-time compiler try to translate it to machine code and run. Okay, that's called just-in-time compiler. You don't compile before you run it. Okay, you don't compile before you run it. You just compile right when you want to run it. And the bytecode is intermediate code. It just finished certain stage, but not really the full compilation. Okay, so this is just in time compilation. Wait until you can no longer wait. Okay, so your code, your source code being compiled to bytecode and loaded to the virtual machine, and then link with the library, and then just-in-time compiler run your bytecode. Okay. Okay, this is Java JDK, Java JRE, and Java version. This is the Java package. Okay, anyway, this is good enough. We know about how Java being compiled. So next one, we are going to do compilation, knowing about the whole compilation process. Okay, so computer programming structure. So there are 6 phases of the compilation: scanner, parser, schematic analysis, intermediate code, machine independent improvement, target code generation, machine specific code improvement. So basically, scanner, parser, schematic analysis, machine independent optimization, target code generation, machine dependent improvement. So this one are called optimization. This one are called optimization. This machine dependent will generate intermediate code. And then you generate target code that's executable. And then you optimize again. So 2 optimization stage. This portion is called front end. From scanner, that's your C language, to bytecode, to some sort of intermediate code, that's called front end. From the bytecode to the machine code, it's called back end. Okay, it's actually 6 stages. So your scanner take character in, created token string. Token string create pass through the parser, become parsing tree, and become syntax tree. Okay, let's look at this. So let's assume that you do have a program is actually class A, okay, public, okay, static, void, okay, and main, okay, and then curly brace string, then right bracket, ARGS, okay, whatever. You write a Java code. You write a Java code. When you see this, this actually is character string. These are character string. This one by one is a character string. So you see CLASS. This is character string. So character string being generated to token string. What is token string? So class is a token. A is a token. Public is a token. Static is a token. Void is a token. Okay, main is a token. And then parenthesis is a token. String is a token. Left bracket is a token. Right bracket is a token. Okay, whatever. You translate from this pure English character to words, meaningful words in Java language. This is become token string. So in the middle, you do need to provide some sort of simple table, so that you know that actually they are tokens. Okay, so like class is a reserved word. You must have that. Otherwise, you cannot generate token. So from token, you're creating parsing tree. So parsing tree means you do have a program, and then you have begin, you have class definition, and main program. And class definition, you have class A. Main function, you start with public, okay, static void or whatever. So your token being distributed in the parsing tree. That is from parser going to the parsing tree. So you create a parsing tree, we call it a parsing tree, and parsing tree decorated with some property that become AST, abstract syntax tree. And then use this AST, we generate the intermediate code. So apparently your language being passed to a tree, and then the tree generate to a intermediate code. So see, we teach you what is a trie, and also teach you how to recursively going through the trie that actually is exercising this abstract syntax tree. Okay, that's the purpose of that project. Okay, and that creates syntax tree. Syntax tree created. Any question? Syntax tree created. You actually created the bytecodes. Bytecode, and bytecode is like Java virtual machine bytecode, and you do some optimization at this stage, and then someday you need to run it on Mac OS. Then you need to create a target code for Mac OS instruction. So that's another stage. That's the so-called just-in-time compiler need to do. Okay. That's the so-called just-in-time compiler need to do. Okay, so these are the 6 phases of the compilation, and our remaining week. Today is week 10, so week 10 to week 16, we are on these things. Okay? We are basically on these things. And then your current project, I also say that anything related to programming languages have some sort of translation will be acceptable. That also means we emphasize you to go through one process of these. Your language can be as simple as rock, paper, scissors. That's okay for me, as long as you do some translation. You know what I'm saying? But I want you to try to go through the whole process of translation, and then that will be a good project. Okay. Okay, these are 6 phases, and then today we are on the lecture 10. We are supposed to look at the tokenization. Okay, so that's actually the first stage called lexical analysis. Okay, stage 1 called scanning is also called lexical analysis. That is converting character to word. So you must know about your basic word meaning units. Now we call it tokens. Valid one in your languages. So class is a class. A is an ID, right? A is an ID, is a ID, a class name. Curly brace is a beginning of certain cobra, right? And then public is a reserved word that's showing that actually is the visibility of the unit. And then static is like the storage class. Okay, something like that. You have to know about lexical analysis, just like you do English. Divide, that's verb. That's article. Program, that's nouns. I mean, something like that. Okay, you need to know. So that's lexical analysis. Is that okay?
Like in a dictionary?
Yeah, you do need to have a dictionary, and you also need to have a grammatical term, such as divide. You need to know about this is a verb, right? Is a verb. Slow is a adjective, right? So you need to process that. So organize your data. So that's so it actually will need to have one program that actually deterministic finite automata. Okay. So in our chapter 10, we'll talk about this deterministic. So this stage is called lexical analysis. Is also called scanning. Scanning is scanning on your words and to convert it to tokens. So it will depend on the deterministic finite automata. So you have a deterministic finite automata that actually is defined as a automata that with state, with a simple set, sigma is a simple set, and Q0 is the initial state, F is the termination state, and the transition table. So this whole thing group to be a deterministic finite automata, okay, and use these to translate your characters to your words, your tokens. Okay, and how it works is in chapter 10. Let's look at chapter 10, lecture 10, I'm sorry. So lecture 10, we will show you lecture 10's tokenization that we will, this is scanner, okay, scanner scanning your call into the tokens, okay, and the way they translate to the tokens is depending on such kind of the deterministic finite automata, something like this, okay? And how it works, we are going to explain it, okay? We are going to explain it, so don't worry right now. You just need to know about it is tons of the finite automata things you need to learn to be able to handle such transition. That's the purpose that we have right here, okay? And translate different language structure. Okay, not that hard so far. Okay? Don't jump to lower there. We will get distracted. Okay, so this is stage 1. You will need to use a deterministic finite automata, and that's lecture 10. Okay, lecture 10. The next one is, okay, we got words. We got words now. We finish the word. Our program become token, okay, words. No longer just symbols. Now you need to have a push-down automata. Push-down automata means that you have a finite state machine including a stack. Okay, including a stack. So you start to create tree using the stack, and we use the context-free grammar to convert it to a syntax tree. So that is second stage is called syntax analysis. We use a push-down automata. So this one is another lecture, maybe lecture 11 or maybe lecture 12. There is a syntax analysis lecture, okay? And then it use a push-down automata. Push-down automata compared to finite state machine, finite state machine is actually also determined to finite automata. Okay, this is a finite state machine. And then push-down automata is like you add stack with it. Okay, that's push-down automata. And you can use with this stack, you can do more. You can do more using the and you can create a context-free grammar. Okay, and we will talk about it later in lecture 11. Okay, anyway, this portion finish the syntax tree, and then the next one will be semantic analysis. Semantic analysis means that grammar is okay. Now let's make sure that it makes sense. So integer a equals 3.4, it doesn't make sense. It doesn't make sense. So semantic violation because you assign the wrong type to integer. Okay? So that's called semantic analysis. So you go through the semantic analysis to find out the syntactic error, okay, and exceptions. And then you actually make sure you have your bug free. After you make sure you're bug free, you use that syntax tree to generate intermediate code. This is stage 4, intermediate form. Okay. And intermediate form finish, you do code optimization on the intermediate program. That's language independent optimization. Then that stage, you generate the machine code. That's code generation. Okay. So these are the 6 phases of the compiler. Okay. But in the middle, you must have 2 things. One is the symbol table. One is the code generation. These 2 things are always there, no matter which stage. Symbol table is always there. A class, A, these are symbol table. Every stage need to be referred to it. Okay, so compiler need to be prepared. Okay, so that's that, and that's actually let's look at front end of a program. Okay, so you front end of a program, you have lexical analysis, syntax analysis, semantic analysis, and then you create the intermediate code. Okay, so the front end compiler. So that's assuming that this is a GCD program in C language. So when you read it in, it is something like this: I as a symbol, N as a symbol, T as a symbol, something like this. Okay, so this one goes through the tokenization stage. So this is the token table. Token, 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 token. Okay, each one of it is a token.
In Python, would they be tuples?
In Python, still tokens. This is actually language independent, still tokens. Tokens just mean word in that language. Is that okay?
Okay, but they wouldn't.
They wouldn't what? Yeah, question. They don't do what?
Is there a token? Is it or would you be saving it as a tuple or a string or
I think it's a string.
everyone's a string?
It's a string, yeah. It's a token. Even if you say J equals 1, it's still a string. It's just a word.
Mm-hmm.
At this moment, it's still not converting to the integer or something yet. It's just a word, just like your English. I am going to the school.
The stream of characters that you're.
So this is one word. This is one word. This stage just do that.
Mm-hmm.
This is one word. Okay, or you say two, number 2, a string. So this number 2 is still a string. It's not integer yet.
Mm-hmm.
Is that okay?
Yeah.
So at this moment, it's not assigning any grammatical meaning yet. It's just word after word after word. So first stage, you are converting a letters character string. Character string means that many characters keep coming. You are converting to word string, token string. And then based on the token string, you go through syntax analysis using the context-free grammar to generate this is context-free grammar for C language for while loop. And then based on the grammar, you generate such a syntax tree like this, that GCD program. Okay. So integer is a type specifier and empty string. And then this is declaration because integer something. Okay. And here you say you're something like that. Okay. So this whole program being translated is such a tree. And that tree, actually, syntax tree, eventually become a declaration. So it actually program equals code. Okay, assignment code. Okay, so phi is here, actually I. So program equals I assigned with, and then sig actually is JJ assigned with while not equal. While not equal phi is I not equal 6, I not equal J. Okay, if greater than I greater than J. So something this is the passing tree of that GCD. And the symbol table is here. So this is the syntax tree. And based on this syntax tree, we generate the machine code. Okay, we generate a machine, intermediate code, I'm sorry, intermediate code. Okay, and these have many stages. There are many lectures to cover it. Okay, at this moment, we just show you the overall flow. And the design of a compiler is from characters to bunch of words to a structured information as abstract syntax tree, and then using backend to generate code. Okay, from bunch of characters to bunch of words to structure information to do something. Okay. So A equal B plus C times D goes through the lexical analysis to become ID equals ID2 plus ID3 times ID4. So A is an ID, B is an ID, C is an ID, times is an operator, D is an ID. Okay, so this is your tokens. And these tokens being converted to a syntax tree, ID equals plus ID plus times ID times ID. That's syntax tree. And then based on this, you use a machine code assembly to translate to load the ID3, multiply ID4, adding ID2, store to ID1. Is okay?
Mm-hmm.
This chart gives you the best idea of what compilation is. Any question? Any questions so far? This chart gives you the best idea. It is a pretty simple chart, but give you the best idea of the stages of the compilation and also what we are trying to do, right? Any questions so far? Nobody has question? Okay. So this one give you the best idea. And yes, go ahead.
I'm wondering how you parse it out with the grammar.
That's using the syntax analysis. Grammar will be converted to syntax analysis. So now, next one is how this lex and yet work. Okay. How grammar being compiled to syntax tree, right? Is okay? That's the next topic we'll talk about.
Mm-hmm.
Okay, let's see. I think this chart has some problem. This chart has some problem. This one is scanner. This is parser, okay? Sorry. This is called yet. This is called lex, okay? So basically, you describe your language symbol rule using regular expression. So no matter what symbol you have, you use a regular expression to actually generate a scanner. So this one is called compiler. If you use a lex can help you to generate a scanner given a certain set of regular expression. Lex, this tool, Lex or Flex. Flex is a PC version of Lex. Okay, we check the 2017 talk. I do teach Flex and Lex. Okay, you can check the 2017-18 video. I teach this at that time. And you take the regular expression description of your language and you will parse it. You're using the Lex to generate a scanner. Now your C language grammar plus the scanner and using yet. Yet is called yet another compiler. So it's YACC, okay? And PC version called Bison. The bison is the animal, okay? It's an animal. So Frag and Bison help to generate the scanner and parser. It will automatically generate from content-free grammar to parser. And with this, you can you include your scanner and parser, you can generate a compiler by using Flex and the Bison. So Frag and Bison are downloadable from internet. Okay, not really hard. Frag and Bison are actually very famous and it's already old. Already old. You can find a lot of Frag and Bison. Okay, this is Frag and Bison. Okay, this many things you can browse through on internet for it. Okay, and Frag and Bison Python version. There's a guy working on the Python version called PyBison. Okay, PyBison. Frag and Bison written in Python. Okay. So here seem to have a question. Okay. Okay. These are the PyBison. Okay. And there's a guy working on this. There's a GNU Bison. Okay. GNU Bison. Okay, anyway, my job is not to go into Frag and Bison right now. Okay, you can check it if you are really interested in using the tool for project. Okay, there are books as well. Okay, now that's actually compiler. Okay, and then you use a Frag and Bison together. You describe your language, your regular expression in calculator.l. L is Lexer. Okay, and then this stage is also called Lexer. Okay, L-E-S-E-R. And calculator y is EC. Okay, and you create simple table and you create lex.yy.c and you use a GCC, you compile and create a calculator interpreter. And it can generate executable code assembly or run it. So run it will become interpreter. Executable code become a program. So this one is how you use the Frag and Bison to generate a compiler. Okay. Or you don't like to use a compiler, you can use the so-called the so-called REPL structure. REPL structure is read, evaluate, print, and look back format. Okay, and REPL format would be the interpreter loop. Okay, interpreter loop. So basically, this is interpreter, and the compiler is using the compilation flow. Okay, so our lecture 10, go back to lecture 10. Our lecture 10 is really on the tokenization, the stage 1, the scanner. Okay, so this lecture 10 is really on the tokenization, how you convert character to the words. Okay, and it's called lexical analysis. And lexical analysis is very important because you have a sentence, you chop it into words. Okay, and then these words need to based on a grammar tree to generate the syntax tree. Okay, so basically, it is also used in natural language processing, text mining, machine learning and AI, information retrieval and searching. Tokenization is the key, very important. So your basic natural language processing stage, first you need to tokenize it. So friend, comma, Romans, comma, countrymen, broken into friend, Roman, countrymen, passing through linguist module, friend, Roman, countrymen, and then using the inverse indexing to generate inverse index for natural language processing, such as grammatical is nouns, something like that, okay? So called indexing pipeline. And then your source code passing lexical analysis generate token, and token actually we talk to the parser produce abstract single tree for the interpreter. Okay, this is a relationship between lexical analysis and parser. And in the middle, you need to have a simple table. Okay, so Python you can use split function to generate the tokenization. You can use a regular expression. You can use NLTK, natural language toolkit. You can use a spacey. You can use a Keras. You can use a Jensen. These are different tokenization tools. Okay, in Python. Okay, so here is tokenization example. Okay, these are okay. So tokenization by split. This is the simplest one. Okay. Simple coding, disadvantage, not good. Okay. So here you read the text and try to strip it and create token. So simplest one is that you just split it into all kinds of symbols. Okay. But the disadvantage is that it doesn't deal with the comma or something wrong with this comma. Also this one. This one is correct. Okay. Here is okay, but this is actually not deal. Okay. So split has some limitation, especially for natural language processing. And then you can do line by line organization. Okay. And okay, line by line. Lexical analysis. Lexical analysis is using the scanner. So to design a scanner, you need to use a regular expression to generate a non-deterministic final automata and use that non-deterministic final automata to determine the words. Okay, so basically it's translating from source code to token list. Okay, and this is a language, and you need to define what is a letter, what is a digit. Okay, what is a left parenthesis? Okay, so this grammar will be written into the regular expression, and we use a scanner to scan it. Okay, so the grammar will be written down as identifier, integer, constant, real constant, command, symbol, something like that. Okay, so there are two types of the scanner. One is EHA scanner. EHA scanner is used. You have the code, and then the programmer directly converted the binary automata into a scanner using coding skill. That's called EHA scanner. And there's another way, it's called automatic generation. So first, it designs such a binary automata, and the programmer directly write it to code. This is called EHA scanner. You can also use in a systematic way to use Lexer to generate. Then that is called the code-generated scanner. So basically, there are two types: automatic generated scanner or EHA scanner. EHA scanner, usually the code is shorter and better. And systematically generated tokenizer actually will be bigger and slower, but it will be usually used for what? For when you don't have any scanner, let's use a machine-generated scanner first. Is that okay? Okay, let's assume that we are looking at this grammar tree. Okay, So here, a keyword would be letter or digit, 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 letter or digit. So it's a letter followed by letter or digit. That is a ID or keyword. Is that okay? So you written down ID or keyword here. You written down number here. You written down assignment here. You written down the basic left parenthesis, right parenthesis as an operator here. You written down the division here. And this actually is the grammar for calculator language. And then after that, you actually try to, okay, this one is a Python version of the lexical scanner generator. It's downloadable from our website, okay? I do give you the source code, okay? And it show you how this lexical scanner is implemented. Okay, so there are different rules, and we try to use a program to generate tokenize, okay, different tokens. We use different rules to generate the tokens one by one, okay. So all of them is in this file called lexscanner.py. Okay, now I have a program like this. And I use my lexscan and generate to here. So this one is a token string. This one is their synthetic symbols. Okay. A is ID, equal is a sign, 1 is number, B is ID, this is a sign, 2 is number, C is C is ID. Okay. Any question? So this token result with tokenization. Any question? Okay. So this is another program. We generate that, okay? Okay, so this is the process, and you have to trace this program. I don't have time to go over it, okay? This is really the big program. And as an example, then that one is a hardcore. Hardcore means that I'm the programmer. I give you the AHA scanner, right? That's called AHA scanner. That's my design. Not systematically generated it. But you can also use regular expression and flex to generate your tokenizer. So basically, compilation stage is that you describe your grammar, your language input, and this grammar being used to generate a state machine. It can be finite state machine, can be push down automata, but your language pass through such a state machine, generate a syntax tree, and then use the syntax tree to generate your topic code, okay? That's what we teach right here. So you need to know about what's regular language and what is regular expression. Okay, this syntax part, that's jump. So this one is using lex and yek. You use regular expression to generate the lex. I'm sorry, the lex, yes. And then you use the yek or Python to generate the parser. And two programs linked together will become your compiler, okay? Okay, here talking about finite state machine, how to design finite state machine and convert it, okay? This portion I'm going to skip, Okay. You need to study by yourself. It's too much detail of the compilation. Okay. So you have to study. It's in the textbook, but not related to coding. So you have to study yourself. Okay. Finite state machine. Okay. And whatever, these are designed of the finite state machine and how to optimize it. Let me see. Okay, let's look at it. So basically, this portion is the finite state machine, and the finite state machine eventually will go to a table that is. So your character in goes through the finite state machine will be generate different grammatical units. Okay. Okay, so you can describe the finite state machine in EBNF format, okay? Extended back nose form, okay? If you describe it in this EBNF format, then you can use Lex to generate the Lex by itself. So basically, you write down your grammar in regular expression. So this one is a regular expression or a email. Okay, for email. So A to Z, underline slash dash. This is the so-called ID, email ID is at some domain name.com, something like that. Okay, 2 to 4 extension word. So CO, CA, GOV, okay, EDU. Okay, this is the regular expression for that. And then that is for email. Okay, that's for email. So username at the domain qualifier. So this is the grammar for regular expression. So using regular expression to actually to qualify your symbols and generate it into words. That's the regular expression. And so if you actually describe all of your language in regular expression, then you can use the regular expression to generate your scanner. Okay? And that's why here we have tons of the regular expression rule. Okay. And there are some websites you can practice the regular expression. Okay. Okay. Today I'm up to here. Any question? So basically, this chapter you need to learn regular expression. You need to learn there are some homework related to regular expression. Okay. If you have problem, let me know. But there are some websites. I'm sure there are some websites you can practice the regular expression.
I actually have a quick question on
Yes.
it looks like that the term project proposal is due this week. How do you want that written up for you again?
A Word or Google Doc for 2-3 pages.
Okay.
But you need to cover the topics such as your project goal, what are you going to do, the way you want to do it, your tool, your software, your reference material,
Okay.
and what you want to deliver.
All right.
Yeah. Any question?
No, that's it. Thank you.
Okay. Any other question? Okay, no question. We are up to here today. Okay. Thank you. Thank you. I'm sorry for being late today. Okay. See you next time. Okay. Bye-bye.
Bye.